Hello, we are Team WMB. On the team is Ed, Ty, Phil, Ben, and I'm Tim. Today we're going to demonstrate the equations of motion. To do this, we've set up a scenario in which the equations of motion will be used to solve a real-life dynamics problem. So in our scenario, Harrison Ford is making a new Indiana Jones movie. In the movie, there's a scene where Indiana Jones has to escape from a pack of rabid monkeys by grabbing onto a rope that is attached to a statue that's been hoisted by a series of pulleys. He will use his bullwhip to knock out a pin that's holding up the statue, and the downward acceleration of the statue will then accelerate Harrison Ford upward to a platform that's several meters above. In order to keep Harrison Ford safe, the stunt director has to use the equations of motion to calculate the mass of the statue, which will be based on the acceleration of Harrison Ford's moving upward. So to describe our diagram, here's Ty.
My name is Ty, and here's our diagram. This is Indiana Jones, a series of pulleys, and here's our statue. SJ represents the length of the cord to Indiana Jones. SS is the length of the cord from here to the statue. To solve this problem, we're going to need our force equals mass times acceleration and our pulley equation. I was thinking about the toothbrush, okay? Don't laugh. It's you laughing, that's the problem. So our pulley equation is the length of the cord equals 3 times the length of the rope from here to the statue plus the length of the rope from here to Indiana Jones. Take the derivative of that and we get that in terms of velocity. Take the derivative again, we get it in terms of acceleration. So then we solve for the acceleration of the statue, which equals negative 1/3 times the acceleration of Indiana Jones. And now here's Ed to explain the calculations to you.
My name is Ed, and I'm going to go over our free body diagrams and work out our equations. So here we have the free body diagram of Indiana Jones. We have down defined as positive, just like we did for our big picture. So his weight acts down and tension is acting up on him, and that is equal to his mass times acceleration, which we defined in the positive direction. Then our free body diagram for the statue is, again, we're being consistent, down is positive. We have the weight of the statue acting down, 3 times the weight, or 3 times the tension acting up due to our pulley setup, and that equals the mass of the statue times the acceleration of the statue. Again, we define that in the positive direction. Our signs will work out if it's in the other direction. So then we start with Indiana Jones and we add up all the forces. So we have gravity in the positive direction and tension in the negative direction, and we set it equal to mass times acceleration, which is the equation we're using. And then I algebraically rearrange this to solve for tension. Then I move on to the statue, and again I add up all the forces and I set them equal to the mass times the acceleration. Then I rearrange to get tension by itself. I get a value for tension by dividing by 3, and then I substitute in our value for the acceleration of the statue in terms of the acceleration of Indiana Jones. So I replaced this AS with negative 1/3 AJ. Then I come over here and I set these two different T's equal to each other because the tension in the cord is constant throughout. So on the left side I have the tension due to Indiana Jones, and then on the right side I have the tension from the statue. Then I multiply the 3 through to the other side, and then I factor out a mass of the Indiana Jones and the 3 so that I have just G minus AJ, and on the other side I factor out the mass of the statue. Then I divide by this value to get the mass of the statue by itself, which gives us an equation we can just plug our values into.
Hi, I'm Ben. So here we've got a setup for you that demonstrates our problem.
off to the left here, we have a force sensor, which will be able to determine the tension in the string. And the weight of this also represents Harrison Ford. Then it follows the string, which is massless string that comes up, around, down and through this pulley, and back around the top to connect right in here. And we've hung a weight here. The combination of both this weight and the pulley are the weight of the statue. So we'll go ahead and run some data here and see what kind of acceleration we get, and then we can plug those all back into our calculations and see if what we've got is accurate. And that's one of the runs, and you would do that multiple times, and then you can go ahead and compare everything and see what kind of percent error you have.
Hi, my name is Phil. From this experiment that we set up here, we were able to calculate and measure an acceleration that was 0.3261 using these motion sensors here. And we were also able to find a measured tension of about 1.342 newtons using this force sensor here. That compared to our theoretical acceleration of 0.3138 and our theoretical tension in the rope that we have here of 1.4264, we had a certain percent error between those two, which was 3.78% error for the acceleration we calculated and measured, and 5.92% for the tension. All of this error is probably due to the fact that we have not completely ideal pulleys, we have motion sensors which have a degree of error in them already, and we have angles between wires where we would like to have no angles at all. So all these things together add up to a small bit of percent error, and in the end we find that our error is less than 10%, therefore it is acceptable, and we have proved our equations. And the stunt coordinator could use this to determine the acceleration of Indiana Jones. Thank you.